Good afternoon, spaceflight enthusiasts. Imagine, just for a moment, that we are looking at the very engine that could make NASA's dreams of reaching Mars, along with any spacefaring nation's ambitions, happen much faster than we ever thought possible, while the rest of the world is still debating chemical rockets that gulp fuel like a hammer on the highway, or nuclear engines that are essentially just fancy hot water rockets. A British company called Pulsar Fusion has just dropped a true world-first breakthrough. It's the kind of news that gets me fired up. And here's a fun fact. I live right here in Milton Keynes, just a stone's throw from where Pulsar Fusion is headquartered in nearby Bletchley. I've had the chance to tour their facilities, walk through their labs, checked out the vacuum chambers, saw the superconducting magnets, and even chatted with the engineers. And let me tell you, this isn't some far-off fantasy. The excitement in the air was palpable, and I could actually smell the ozone in that lab, which tells you that this is real, cutting-edge stuff. So, on March 25th, 2026, just 3 days ago, Pulsar Fusion hit a massive milestone. They fired up the first plasma inside their Sunbird nuclear fusion rocket exhaust system. This was live-streamed directly to Jeff Bezos' exclusive Mars conference in California, where the company's CEO, Richard Dine, presented it to a room full of Nobel laureates, astronauts, and AI pioneers. This wasn't a dusty prototype. No, this was the actual exhaust architecture for a fusion propulsion engine that could reduce the time it takes to get to Mars from 7 months down to as little as 45 days, or perhaps even less than that. And it could get a probe to Pluto in just about 4 years instead of decades. Today, we're diving deep into what Pulsar Fusion has just achieved, the history of the company, the mechanics behind the Sunbird dual direct fusion drive, and why this is the propulsion system that will change the game, not just for NASA, but for space exploration as a whole. And I'm going to break it all down without any fluff. Now, you might be wondering, how is this any different from the nuclear electric propulsion systems NASA is working on, or the Wassermeer thruster, which is considered the next big thing? Well, this is where things get really interesting. We'll explore how Pulsar's fusion drive absolutely outclasses these other technologies in every way, and why this successful plasma test is such a major engineering milestone. There are still hurdles ahead, but we're on the cusp of a paradigm shift in space travel. Buckle up, because this is a thrilling ride into the future of space propulsion. If you're as excited as I am, smash that like button and let's dive into the story behind Pulsar Fusion and its game-changing technology. Now, let's take a step back for a moment and look at who Pulsar Fusion really is. It's easy to think of them as just another tech startup, but that couldn't be further from the truth. These guys have been putting in the work since 2017, steadily progressing from smaller experiments to fully embracing the challenge of fusion-powered space propulsion. And it's not some fly-by-night operation. This is a company that has already made significant strides in the field, and I've seen the proof myself. Their headquarters in Milton Keynes is located in a small industrial unit that, on the surface, might seem unremarkable. But inside, it's a different story. The place is packed with cutting-edge equipment, vacuum chambers, high-power magnets, and plasma diagnostics at every turn. The team here is small, but laser-focused, moving fast, and completely unencumbered by the bureaucratic red tape that so often slows down big government-backed projects. When I visited, I was genuinely impressed by how they were tackling some of the toughest engineering challenges out there. Richard Dine, the CEO, has been in this fusion rocket game for years, and when you talk to him, it's clear that he's a true believer in the potential of fusion propulsion. He's convinced that fusion propulsion could be the key to interplanetary travel and that it could actually be developed before fusion power plants for Earth. Now, I've seen the hardware up close, and after touring their facilities, I believe him. Pulsar Fusion's journey hasn't been without its challenges. Fusion propulsion is notoriously difficult to make work, but they've tackled these obstacles head-on, securing serious funding and forging partnerships with key organizations, including the UK Atomic Energy Authority, to work on neutron shielding. And they're moving quickly. Their flagship project, Sunbird, is a reusable 30-meter long space tug designed to dock with cargo ships in orbit, think Starship. But for propulsion, the idea is simple. Light up the fusion drive and travel across the solar system with minimal propellant, much less than the chemical rockets we rely on today. With Sunbird, you could make a trip from Earth to Mars in just 45 days, half the time it currently takes with chemical rockets. On March 25th, as I mentioned earlier, Pulsar reached a huge milestone with the live stream demonstration of their first plasma test inside the Sunbird's exhaust system. It was the first time anyone had ever successfully created, guided, and contained superheated plasma inside the exhaust channel of a fusion-powered rocket. This is no small feat. Plasma, the charged particles that power fusion propulsion, is notoriously difficult to control. It's hot, about 100 million degrees Celsius, and unstable. Getting it to stay contained without frying everything it touches is one of the biggest challenges engineers face. But Pulsar did it. And they did it live, remotely from the UK, while Richard Dine presented it to a global audience at Bezos's Mars conference. This wasn't just CGI or some conceptual demo. This was real engineering happening right in front of our eyes. The test was a success, and it proves that the core exhaust system works. Static fire tests are next on the agenda, and while they initially aimed to complete those last year, it's looking like they'll be ready in the near future. Once those are complete, they're targeting a full in-orbit demonstration by next year. But to be honest, I think even that might be a bit optimistic. Still, it's clear that Pulsar Fusion is on track to make fusion propulsion a reality much sooner than anyone had anticipated. So, why is this such a big deal? Because it's not just a step forward, it's a quantum leap. They're proving that fusion can work as a propulsion system in space. For decades, scientists have been talking about fusion as the holy grail of energy, but no one has successfully demonstrated it for space propulsion until now. Pulsar is showing that it's possible, and that's a game changer. Now, let's break down exactly how Pulsar Fusion's Sunbird propulsion system works. To start, Sunbird isn't just another rocket engine, it's powered by what they call the dual direct fusion drive. This is where the magic happens. Instead of relying on traditional chemical or nuclear thermal propulsion methods, the Sunbird uses fusion to generate both power and thrust. And when I say fusion, I'm not talking about the fusion power plants that have been just 10 to 20 years away for the last half century. No, this is fusion used directly to propel a spacecraft. The system operates with two compact linear fusion reactors running in tandem. They use a fuel mix of deuterium, a form of hydrogen and helium-3, which creates an aneutronic reaction. In simpler terms, this means that the fusion reaction produces energy without the harmful neutrons that can damage the engine and the crew. Instead, it generates fast-moving protons and helium nuclei, which are far cleaner and more efficient, producing significant amounts of energy without the dangerous radiation. Step 1 in this process is using rotating magnetic fields to heat up and spin the plasma inside a field-reversed configuration. Imagine this like a smoke ring made out of a 100 million degree ionized gas that floats in midair without touching the walls of the reactor. That's the plasma. This heated plasma is where the magic of fusion begins. When you heat plasma to such extreme temperatures, the fusion reaction kicks off, releasing energy in the form of charged particles with insane kinetic energy. These superheated particles are ionized, meaning they can be controlled by electromagnetic fields. Once the plasma reaches this stage, the charged particles shoot out one end of the reactor and get funneled through a magnetic nozzle diverter. This nozzle, lined with superconducting magnets, shapes the exhaust and directs it like a precision laser, ensuring that all the energy is harnessed efficiently for thrust. At the same time, Pulsar injects additional neutral propellant into the exhaust, like hydrogen. The fusion exhaust heats up this propellant, causing it to expand rapidly and provide additional thrust, a process known as thrust augmentation. This is a key advantage of the Sunbird system. It's not just about the fusion reaction itself, it's about combining fusion efficiency with additional push from the extra propellant. The performance numbers are impressive. The exhaust velocities on this ionized plasma range from 110 to 350 kilometers per second, which is orders of magnitude faster than traditional rocket exhaust. But here's the kicker. They don't need to generate more energy than they use. The plasma naturally moves that fast. Previous targets for exhaust velocities were around 223 kilometers per second, with specific impulses between 10,000 and 15,000 seconds, 20 to 30 times better than chemical rockets and far superior to nuclear electric propulsion systems. And that's not all. The Sunbird system can also deliver up to 2 megawatts of electrical power to the spacecraft, which can be used for life support, science instruments, or even beaming data back to Earth. This makes Sunbird a true dual-output engine, delivering both thrust and electricity from the same compact package. No massive radiator panels or external power sources like you'd find with traditional nuclear electric propulsion systems. The entire system is sleek, efficient, and scalable. One of the most exciting aspects of the Sunbird system is its design. The Space Tug is built to stay in orbit permanently. It can dock with cargo ships like SpaceX's Starship, refuel with tiny amounts of deuterium and helium, 3 literally grams, not tons, and then undock and travel across the solar system with almost no propellant mass compared to chemical rockets. This makes it the ultimate space taxi for the solar system, capable of ferrying both crew and cargo to destinations as far as Mars, Jupiter's moons, and beyond. But while the Sunbird system is revolutionary, what sets it apart from other propulsion systems on the market? How does it compare to NASA's Nuclear Electric Propulsion (NEP) plans, or the Wassermeer, the advanced plasma thruster developed by Ad Astra? The answer lies in the numbers and the fundamental difference in how these systems generate thrust. So, let's take a deep dive and compare Pulsar Fusion's Sunbird system head-to-head with some of the other propulsion systems that are currently being developed. First up, we have NASA's Nuclear Electric Propulsion, NEP. This is the propulsion system that NASA is betting on for its upcoming Mars missions, and it's already generating quite a bit of buzz. The idea behind NEP is simple. Use a nuclear reactor to generate electricity, which then powers an ion engine to generate thrust. The main advantage of NEP is its high specific impulse, meaning it can operate efficiently for long durations. But there's a catch. The thrust is incredibly low. NASA's Space Reactor 1 Freedom mission, launching potentially by the end of 2028, will use NEP to power its journey to Mars. It will employ nuclear electric ion thrusters, which generate electricity from a nuclear reactor to provide continuous low-thrust propulsion. However, even with all the power it will have, the spacecraft will still have very low thrust, meaning it will take between 6 to 12 months to get to Mars. For crewed missions, that could be a serious issue. given that radiation and microgravity on long flights pose health risks. So, while NEP is a step forward, it's still far from ideal when it comes to reducing transit times and ensuring the safety and comfort of astronauts. Then, we have the VASAMER, or the Variable Specific Impulse Magnetoplasma Rocket, developed by Ad Astra. This advanced plasma thruster is impressive in its own right, using radio waves to ionize and heat plasma, then using magnetic fields to accelerate it. The prototype of the VASAMER, the VX200, has already shown that it can achieve an impressive specific impulse of up to 30,000 seconds, with exhaust velocities ranging from 15 to 100 kilometers per second. But again, there's a major drawback: low thrust. The VASAMER still requires a massive external power source, usually a nuclear reactor, and huge radiators to handle the power. And even when scaled up, the system still struggles with providing enough thrust for quick interplanetary missions. This is where Sunbird really starts to shine. Unlike both NEP and the VASAMER, Sunbird's fusion propulsion system is direct. The fusion reaction itself generates both power and thrust, meaning there's no middleman reactor converting electricity to thrust. The result? Higher exhaust velocities, a dramatically better thrust-to-power ratio, and a much more compact and efficient system overall. According to Pulsar, their fusion drive is 100 times better than current electric systems in practice. What does this mean for travel times? The Sunbird system can provide the kind of thrust necessary to drastically shorten travel times. Mars, which would take 6 to 12 months with NEP, could be reached in just 45 days or less. And that's not just theoretical. This is the kind of performance that makes human exploration of the solar system a practical reality. Imagine getting from Earth to Mars in less than 2 months instead of waiting half a year or more. This is the kind of breakthrough that will redefine space travel. Another huge advantage of Sunbird is the minimal propellant mass required. Unlike chemical rockets that burn massive amounts of fuel to achieve even a fraction of the thrust needed for long-distance space travel, Sunbird uses fusion to generate thrust efficiently without needing a huge amount of fuel. This opens up new possibilities for long-duration missions where the spacecraft can keep its propellant load light and focus on completing the journey rather than constantly worrying about running out of fuel. The icing on the cake? Sunbird's fuel is a neutronic blend of deuterium and helium-3, which produces far less radiation than traditional fusion fuels, making it far safer for both the crew and the spacecraft's electronics. The result is not just a more efficient propulsion system, but one that poses fewer risks in terms of radiation exposure, which has been a major concern for previous fusion propulsion designs. In short, Sunbird isn't just another propulsion system, it's a game changer. Compared to the options out there today, whether it's chemical rockets, nuclear thermal propulsion, or even nuclear electric propulsion, Sunbird is faster, more efficient, and far more capable of supporting long-term crewed space missions. And the best part? It's not some pie-in-the-sky concept, it's happening right now. But let's take a moment to explore what's next for Pulsar Fusion and their Sunbird system. While the recent plasma test was an undeniable success, there's still a long road ahead. This isn't a fully operational system just yet. There are hurdles that must still be overcome. The next steps involve fine-tuning the technology and pushing it to full power. The team at Pulsar is moving fast, but they aren't rushing things. One of the next big milestones will be static fire tests, where they'll ignite the fusion reactor and hold it steady for extended periods to ensure everything remains stable under continuous operation. Following that, they'll be aiming for an in-orbit demonstration of the core technology, which could take place as soon as next year, although there is a lot of work to be done before that becomes a reality. But here's the real kicker. Even though these tests and demonstrations are coming, the science is already proven. They've shown that they can create and control superheated plasma inside the exhaust system, and that's the key. It's not theoretical anymore. They've done it. And once they perfect the system, we could be looking at a fully functional fusion propulsion engine much sooner than anyone expected. The potential applications are massive. Imagine, for instance, NASA's Mars missions with Sunbird propulsion. In addition to dramatically shortening travel times, the system could make the entire trip more efficient with less fuel and fewer radiation risks for the crew. It could be the perfect solution for long-duration missions, whether it's getting humans to Mars, sending probes to the outer planets, or even opening up the possibility of missions to places like Jupiter's moons or beyond. And here's where things get even more exciting. While Pulsar Fusion is still working on scaling up the technology, the company's approach is refreshingly similar to how SpaceX operates. They're iterating quickly, learning from each test, and moving forward at startup speed. When you compare this to the slow bureaucratic pace of traditional space agencies, Pulsar's speed is nothing short of impressive. With new partnerships and funding secured, they're tackling problems head-on and making rapid progress. Now, I won't sugarcoat everything. There are still challenges. For one, helium-3, the fuel that powers the Sunbird system, is relatively rare on Earth. It's something that can be mined from the moon, but that's a whole new challenge in itself. NASA has already set its sights on lunar mining as part of its long-term plans, so this could align well with future space exploration goals. Additionally, Pulsar will need to scale up the fusion system to deliver even more power and thrust, which will require further testing and development. Plus, there are the regulatory hurdles of launching a nuclear-powered system into space. All of these challenges are significant, but Pulsar is tackling them with the kind of agility that's necessary to make breakthroughs. But that's not all. NASA's nuclear propulsion plans, including the Space Reactor 1 Freedom mission, are set to launch by the end of 2028. This mission will use nuclear electric propulsion to get a spacecraft to Mars. However, that system is still relatively slow and inefficient compared to Sunbird's direct fusion drive. If Pulsar's technology continues to evolve at its current pace, they could easily be the next step after NASA's nuclear electric propulsion systems, offering faster travel times, less fuel usage, and more efficient power generation for deep space missions. In fact, Pulsar's fusion propulsion technology could fit perfectly into NASA's long-term goals. The Space Reactor 1 Freedom mission will help to demonstrate how nuclear electric propulsion can work for Mars missions, but once that milestone is reached, the next logical step will be fusion, and that's where Pulsar's Sunbird comes in. It could cut the travel time to Mars to 150 days or less, reducing the radiation exposure for the crew and providing crucial onboard power for scientific instruments and life support systems. With fusion propulsion, we can finally envision a sustainable, regular pathway for human exploration beyond Earth. This is exactly the kind of game-changing technology that NASA needs to make human space exploration a reality. Sunbird could be the key to making Mars missions faster, more efficient, and safer for astronauts. But even beyond that, it could open up the entire solar system for exploration: Jupiter, Saturn, the outer planets, and even the moons of distant worlds. The possibilities are endless. As we look to the future, it's clear that Pulsar Fusion's Sunbird system is on the cutting edge of space propulsion. And it's not just a dream, it's a tangible reality that's slowly coming to life. The fusion propulsion system they've developed is poised to drastically change how we think about space exploration. If all goes according to plan, we could see operational Sunbird fusion-powered spacecraft within the next decade. Think about that for a moment. Permanent orbital transfer vehicles that can ferry cargo and crew from Earth to the Moon, Mars, and beyond, all with minimal fuel requirements and much shorter travel times. This isn't science fiction, it's the near future. But even with all this potential, there are still challenges to overcome. Helium-3 is rare, and securing a steady supply will be critical to the long-term success of fusion propulsion. Fortunately, as I mentioned, NASA has already laid out plans to mine helium-3 from the moon, so the infrastructure for this could be in place just when Pulsar needs it. Additionally, Pulsar will need to refine and scale up the technology, ensuring that the Sunbird system can handle the power demands of full-fledged space missions. They will also have to address regulatory and safety issues regarding the use of nuclear technology in space. But with the progress they've made so far, I'm confident that they'll continue to break down these barriers. What's also exciting is the broader impact this could have on space agencies around the world. If Pulsar can deliver on its promise, it could not only change NASA's approach to Mars exploration, but also influence how other spacefaring nations design their interplanetary missions. The ability to shorten travel times, reduce fuel costs, and lower radiation risks for crew members could make deep space exploration more viable and sustainable than ever before. It's the kind of technology that could open up the solar system to regular, reliable travel. And that's something we've all been waiting for. Looking ahead, NASA's own efforts in nuclear propulsion, including their Space Reactor 1 Freedom mission, will serve as a stepping stone. But Sunbird's fusion propulsion system could be the catalyst for a whole new era in space exploration. Imagine Artemis moon base crews hopping aboard the Sunbird tug, traveling directly to Mars without months of arduous space travel. Think about how much faster science probes could reach distant moons like Europa or Titan without taking decades to get there. Sunbird could be the key to making these missions feasible in the not-too-distant future. And let's not forget the implications for private space companies like SpaceX. If they're able to tap into fusion propulsion, we could see a revolution in space travel, not just for astronauts and cargo, but for everyday space tourists too. Fusion propulsion could make it possible to send people to Mars and beyond more quickly, efficiently, and safely than ever before. This is a paradigm shift that could change everything from deep space exploration to commercial spaceflight. As we move forward, the excitement is palpable. We're witnessing history in the making as Pulsar Fusion pushes the boundaries of what's possible. They've shown that fusion propulsion isn't just a theoretical concept, it's a technology that's rapidly becoming a reality. The first plasma test was a major milestone, but it's just the beginning. If Pulsar continues to hit its targets, we could see the Sunbird system powering space missions within the next 10 years, forever changing the way we explore the solar system. So, what's next? Well, we're all waiting to see if Pulsar can continue to deliver on their promises. If they can scale up the technology and overcome the remaining challenges, we could be looking at a future where fusion propulsion becomes the standard for space travel. It's not just a dream anymore, it's a real possibility, and the race to space has just taken a giant leap forward. If you're as excited about the future of space travel as I am, don't forget to like this video, subscribe, and hit that bell for more updates on the latest in space propulsion technology. Drop your thoughts and questions in the comments below. What do you think about the potential of fusion propulsion? Is this the future we've been waiting for? Let's talk about it. Thank you for tuning in, and until next time, stay curious, stay inspired, and stay angry about space.